Welcome to today's Explainer. I am absolutely thrilled to guide you through this topic today, mostly because, well, it's something every single one of us relies on literally every day, yet hardly anyone actually understands how it works. Today, we're going on a little trip. We are tracing the journey of a single watt. We're going to demystify the incredible, totally hidden hardware and the fascinating chemistry that powers our smartphones. Honestly, by the end of this explainer, you're going to look at that little white block plugged into your wall in a completely different light.
Okay, let's dive into this. When you plug your phone in at night, or maybe you drop it on a pad that uses electromagnetic induction for wireless charging, it's super easy to think of that charger blocking cable as just a simple dumb pipe, just moving electricity from point A to point B, right? But that couldn't be further from the truth. That totally common, everyday charging block is actually a marvel of dense, high-speed engineering. It's doing this highly dangerous, intricate dance with electricity just to keep your device safe.
So here's our roadmap for today. First, we'll look inside the power brick. 2, we'll cover the optocoupler safety switch. 3, the CCCV charging profile. And 4, protecting your battery life. Let's get right into it.
Section 1. Inside the power brick. The sizing trick.
Have you ever actually wondered why we even need a brick in the first place? Like, why can't we just run a direct wire from the wall outlet into your phone? Well, it all comes down to a switched-mode power supply, and the conversion process is, frankly, entirely counterintuitive. It happens in 3 main steps. First, the 220 or 110-volt AC power from your wall hits a bridge rectifier and becomes fluctuating DC. But we can't really use that yet. Step 2, an oscillator circuit takes that DC and actually turns it back into AC. Crazy, right? Finally, a transformer steps down the voltage, and a diode and capacitor smooth it all out into the nice stable 5-volt DC your phone craves. So why go AC to DC, back to AC, and then back to DC again?
The answer is all about frequency. You see, the AC power coming out of your wall is pulsing at a relatively slow 50 or 60 hertz. If we tried to step that down directly, the physical transformer and capacitors you'd need would be massive. I mean, literally the size of an actual house brick. But by converting the power inside the charger to high-frequency AC, somewhere between 15 and 50 kilohertz, which is thousands of times faster than your wall outlet, engineers can drastically shrink the size of the components. That brilliant little frequency shrinking trick is exactly why your charger can easily fit right in your pocket.
Section 2. The optocoupler safety switch. The handshake. Now, what's really interesting about this slide is understanding how we keep all of this safe. With power switching on and off thousands of times a second, what prevents some random glitch from sending wall-level voltage straight into your phone and absolutely frying it instantly? Well, there needs to be a feedback loop. Think of it as a handshake between the input and the output. If the high-voltage side and the low-voltage side were physically connected by a normal wire, a surge could just cross right over. Enter the optocoupler. This tiny little component has an infrared LED on one side and a phototransistor on the other, and they are separated by a physical gap. They communicate entirely through light. There is absolutely zero physical electrical contact between the two sides. Here's how this light-speed safety switch works in practice. The secondary side of the transformer is constantly keeping an eye on the output. If the voltage starts creeping just a bit past a safe 5 volts, a component called a 4.2-volt Zener diode kicks in. This immediately turns on that infrared LED inside the optocoupler. The light shines across the tiny gap, hits the phototransistor, and instantly triggers the primary circuit to just halt the flow of current, cut it off entirely. The very moment the voltage drops back to a safe level, the light goes out and charging resumes. It is just this elegant, continuous safety loop happening in real time right inside that little brick. Moving right along to Section 3, the CCCV charging profile, the battery's thirst. Okay, so now that the power is safely delivered, how does the phone actually handle it? Lithium-ion batteries are incredibly energy-dense, and great news, they have no memory effect, but they are also really delicate. You can't just blast them with electricity. They have to kind of drink it safely using a very strict set of rules. Before the battery even gets the charge, the phone's internal charger IC has to manage it. Now, tiny IoT devices, they use simple linear chargers that take less than 500 milliamps. But for our modern smartphones that need massive amounts of power, we rely on switching chargers. These utilize inductors, and they're absolutely essential for handling the high currents required for modern fast charging.
And this brilliantly illustrates exactly what we're talking about. This is the constant current, constant voltage, or CCCV, charging profile. It dictates exactly how the battery drinks this power. Let's look at the x-axis for time and the y-axis for voltage and current. Now, if a battery is deeply depleted, it has to start with a tiny little trickle charge or pre-charge just to safely raise the voltage, because if you blasted a completely dead battery with full power, you'd permanently damage the cells. But once the battery hits around 3 volts, that's when the real magic begins.
Let's move to the next phase, constant current, or CC. I want you to think of this phase kind of like pouring a beer into an empty glass. Because the glass is totally empty, you can open the tap wide and pour fast without worrying about it spilling over the sides. This is the fast charge phase. The charger allows high currents, typically between 0.5C and 3C depending on what the battery is rated for, to just pour right into the phone. And as it does, the voltage steadily rises as the battery capacity fills up.
But, as you know, you can't keep pouring a beer at full speed when the glass is almost full, right? That brings us to the constant voltage, or CV phase. Once the battery reaches its upper voltage limit, which is usually somewhere between 4.1 and 4.5 volts, the charger locks that voltage strictly in place. It basically acts as a ceiling. So to prevent overflow and permanent cell damage, the current exponentially decreases to a very careful trickle. The whole charging cycle only completely terminates when that current drops below a specific threshold, which is usually about 10% of the battery's total capacity.
Section 4. Protecting your battery life, the human element.
So how does your daily routine actually interact with all this delicate science? Well, the experts outlined several key habits that directly impact the health of your lithium-ion battery. The most famous one is probably the 20-80% rule. Remember that CC/CV profile we literally just looked at? Fully draining a battery to zero forces it into a delicate trickle charge recovery state, and pushing it all the way to 100% holds it in a high-stress constant voltage state. By partially and frequently charging, basically just keeping it between 20% and 80%, you are keeping the battery in its absolute most comfortable, efficient state. Oh, and you should definitely decrease your screen brightness and reduce your screen auto-lock timeouts just to minimize any unnecessary battery drain.
Furthermore, if there is literally one thing you take away from this explainer, please let it be this. Heat is the absolute worst enemy of lithium-ion batteries. Extreme cold might temporarily reduce your battery capacity, sure, but heat physically degrades the battery chemistry. Leaving your phone in a hot car or out in direct sunlight, it's completely disastrous. And this is exactly why you should avoid using heavy apps while charging. The switch mode power supply we talked about is already generating heat. Stacking intensive, heavy app usage right on top of that causes the device to overheat, which drastically shortens its lifespan.
So the crucial point is how you connect to the wall. But actually, before you go blaming your cable for a slow charge, check your phone's port. Seriously, a super common issue is a charging port that's just clogged with pocket fluff. A simple wooden or plastic toothpick can gently scrape out that debris. Just please, never use metal tools like a SIM pin or you'll permanently scratch and damage the internal metal connectors. But if the port is clean, hardware absolutely matters. When you use cheap, counterfeit cables and third-party chargers, you are very often completely bypassing the brilliant safety engineering we just explored. Those cheap chargers are made of inferior materials, and they usually lack those vital feedback loops like our optocoupler friend required to safely cut power if the voltage spikes. Using them puts both your battery and your phone in very serious danger.
While we followed the watt from the wall outlet through the high-frequency switching and light speed safety checks of the power brick, and finally into the carefully managed chemical profile of the battery itself, it really is a massive marvel of modern engineering that happens every single day right there on our nightstands. So I want to leave you with this final question to think about. Based on the science we've uncovered today, are your daily charging habits helping or are they hurting your battery? Thank you so much for joining me on this explainer, and I really hope this knowledge empowers you to get the absolute most out of your devices.